Hello. Thank you very much for joining, wherever you are. My name is Lior Ella. I'm a researcher at Quantum Machines, and my background is in condensed matter physics, and I've joined Quantum Machines about 3 years ago. I'll be giving a talk today together with Arthur Strauss, who is also at Quantum Machines, who is also a physicist who did his bachelor's and master's at EPFL, also on quantum physics. Okay, so thank you very much for joining. So what we're going to be talking about today is breaking the barriers of experimental quantum error correction with a quantum orchestration platform. Okay, so what does that mean? And what are we going to show today? So we're going to start by talking about the basic ingredients of quantum error correction in a nutshell. What we need in order to understand the big problems. And then we're going to talk about the challenges that arise when you implement quantum error correction experiments on real hardware. And then how the quantum orchestration platform provides a unique way to overcome these challenges. And we're going to see it on 2 different Qubit platforms. Okay, so let's get started. So in order to understand the basic idea, let's start by discussing a specific problem in quantum error correction, a basic problem, which is state preservation. Okay, so if we're running a state preservation experiment, what we're actually going to do is to take many physical qubits, and we're going to initialize them to, and then we're going to basically encode on them one, in this case, in our example, one logical qubit on some arbitrary state. And then we're just going to wait in the logical space, meaning we're going to do a logical identity operation. Then we're going to measure the state and do a decoding operation in order to understand what we actually measured. And then this decoder is going to give us either 0 or 1. And the probability of getting 0 or 1, if we were successful, should correspond to this alpha absolute value square. Meaning the distribution that we intended to get with the state. Okay, so a few basic things is that the longer we wait, the lower the probability of success is going to be, and also this is a basic ingredient of fault-tolerant quantum computation, meaning this is like the identity operation, right? So you must be able to do this in order to progress to more difficult things, like for example, playing gates, logical gates. Okay, so this seems fairly simple, but let's go under the hood to see what is going on, and we'll see that it's actually quite involved. So the first thing is to initialize the state. Now, this may seem straightforward, but it's actually not very straightforward if you come to think about it, because you need to take a lot of qubits, a lot of these physical data qubits, and put them all in the ground state at the same time. And that basically requires playing conditional reset pulses. But then once you start playing conditional reset pulses on many qubits, you run into all sorts of problems on what is the optimal strategy to do that. Okay, and it's not a simple question, what is the optimal strategy to do that? But one important thing is that you need a control scheme that is flexible enough to allow you to test out different ideas and different implementations. Okay, and this is going to be a common theme throughout this talk. And now we can already see it in the initialization stage. The next thing is a preparation of the state or encoding of the state. This is, here we see an example where actually in this example that I took from a paper, we're encoding the state minus and 1. Okay, so there are 2 logical qubits here, encoded on 4 physical qubits. So here we're playing all of these gates in order to encode the state, and it needs to be done in a fault-tolerant way. Then we get to the logical wait part, which on the logical level, as we said, nothing is happening, but actually a lot is happening on the physical level. So here we see an example from a paper by Google where they are doing this logical wait on a repetition code, and that we're going to discuss soon. And you see here that you're playing all these Hadamards and you're playing these control Z gates, and you see that some of these qubits are constantly being measured. So these are measured operations, and this is being repeated. And these qubits are called ancillas. They don't actually store the information, but they are used in order to perform the error correction. And you see that after they're measured, they need to be reset. And there's also dynamical decoupling sequences going on here. So it's very complicated. Like there's a lot going on. And what is actually going on here is not trivial, okay? It's not something that you could have foreseen that you would want to do all of these things a priori, okay? So another thing to understand is that as this goes on, basically these ancilla measurements that we talked about, their measurement results, which are called syndromes, go into this classical syndrome memory. And then the final state of the data qubit is measured, and the result of the measurement goes into the classical data memory. Then both of these are fed into the decoder, and the decoder is going to give us either 0 or 1. Okay, so that's the basic idea of a state preservation experiment. And as we said, if we succeeded in the experiment, the 0 or 1 should have a distribution that came from this logical state. Okay, awesome. So now we're going to focus on the logical weight part, and we're going to show that the flexible and ultra low latency controller is actually a crucial ingredient in a successful state preservation experiment. And in order to do that, let's first dive in a bit more deeply into the logical weight part with an illustrative example. So this example is a repetition code in transmods. And in this example, what we're going to do is we're going to take our bit and we're going to stretch it. We're going to repeat basically the 0 state into 3 zeros and then the 1 state into 3. We're going to encode it in 3 qubits. This is the simplest code. And it only protects from bit flip errors, but it shows the basic principles that arise in more complicated codes. And what is the basic principle here? So let's say that we had this error that came in and our qubit flipped the state. Okay, so one of the qubits flipped the state. So now we have these 0, 0, 1 and 1, 1, 0 instead of all zeros and all ones. And here in this situation, if we just look at this and we can see that, well, we could have known that this happened because still the majority of qubits here are 0 and 1. So so the most likely thing is that this qubit flipped when we look at this. And it's actually the correct thing unless we're in a situation where 2 qubits flipped, and then we wouldn't have been able to see this, okay? So, but the problem is that in quantum computing, you can't actually go and look at the state because you're going to collapse it. So the trick is that instead of directly measuring the state, we're going to measure the parity of pairs of qubits, okay? And then we're going, and this measurement does not reveal to us what is the actual quantum state. Okay, if you go through the calculation, you will see that. And the important thing is that in order to be able to do this trick, we need additional qubits and control hardware. Okay, so in this specific case, the parity pairs are going to give us, instead of even, we're going to get even-odd parity. Okay, and more generally, if we have either one of those 4 available syndromes, it means after we measure these syndromes that it definitely like conclusively means that the 3 data qubits collapsed into one of these one of the Hilbert spaces that are spanned by these pairs of states. Okay, so if, for example, we had even-odd, we know for a fact that the qubit states have to be spanned by this subspace. Okay, so this is the basic idea of quantum error correction. Okay, so now we want to look at this in the context of multiple measurement rounds. Okay, so here we see a circuit that implements this error correction, and you see that we have these data qubits and these ancillas. And ancilla 0 is going to measure here the parity between D0 and D1. Ancilla 1 is going to measure the parity between D1 and D2. And then we're going to perform these measurements and put this in the ancilla memory. Okay, so let's look at it in practice. Let's see what's actually going on when we run this circuit. So first of all, this repeats itself many, many times, right? And here we're actually kind of zooming in on a single 2 data qubits and a single ancilla, which is the most basic building block of this this code. And here I also put this plot from another Google paper where this experiment was performed in practice. So which shows basically what we explained before, that we introduce the state and we encode it in these data qubits, and then we repeatedly perform these parity measurement cycles. And the result, we feed in to a decoder together with the final result to recover the statistics of the final state. Okay, so here we're looking in this plot. We're basically looking at, for example, this subset of this code. Okay, so what happens when we have an error? Let's run through it. So let's say that we had a run where the only error that occurred is this measurement, is this data qubit error here. So what will happen? So in the first two syndromes, we're going to, let's say that we started with zero parity, okay, with even parity. So in the first two syndrome records are going to give us 0 and 0. Now, this qubit is going to be flipping its parity. So on all subsequent CNOT operations are going to flip the state of the data qubit, of the ancilla. So now what's going to happen is that this CNOT is going to flip the ancilla and we're going to measure 1, okay? Then it's going to flip it again, we're going to measure 0. Then it's going to flip it again, and we're going to measure 1, okay? Repeating this, we see that we now get an alternating pattern which alternates between 0 and 1. Another such scenario is a data qubit ancilla error occurring. Here, we're going to get first two measurements of 0, assuming we're in even parity. Then, throughout all the rest of the measurements, we're going to measure 1s, okay? Now, already we can see here that there is something which is not optimal because the errors in this circuit are going to be larger if the ancilla is going to be in the excited state because of T1 decay and other factors. So this is already kind of suboptimal. So we can see that there is a slight problem here. But before we go into that in more detail, let's look again at the big picture. Okay, so let's say that let's look at the entire circuit and a specific run where we had this measurement error here, and we had a measurement qubit or ancilla qubit error here. Here we had a data qubit error. And if you go through this, you will see that this is the specific record of syndrome measurements that occurred. Now, it's not important what is the actual record in this case, but the point is that you get this record, okay? And you get, in the end, you do this final measurement, which gives you these measurement outcomes for the data qubits. And then you take all of this, you feed it into the decoder, okay? And the decoder, if it's successfully decoded, it's going to tell us that D0 had no errors, D1 had a bit flip error, and D2 had no errors, okay? And this is the best the decoder can do in this situation. And if you're interested in learning more about decoding algorithms, then here's some references. So there are several decoding algorithms. The traditional one or the original one that was discussed in the context of surface codes, for example, which are like 2D versions of this essentially, is the minimum weight perfect matching decoding algorithm. Then we have more recently algorithms that are based on neural networks and renormalization group, and this is it's an active field of research. But what I want to emphasize here is that the quantum orchestration platform, because we have the pulse processor engine, which is a full processor that runs in parallel with the execution of the pulses, it allows us to do real-time decoding of the measurement record and to run the decoder in parallel. And this is a very important feature that we have in our hardware. And if you would like to explore this and understand more how it works, then feel free to contact us and we'll be happy to work with you on that. Okay, now the thing is, okay, that if you actually go and run this experiment, you're going to see that you will quickly run into big problems because of the way the quantum hardware actually operates. Okay, so previously I said that we're talking here about transmons, and transmons are they have unique properties that come with them. So, for example, there is leakage to the F state or the 2 state, among other things, right? So here we're kind of summarizing different things that actually are going wrong in this experiment. So the first one, and this is all taken, by the way, from a Google paper that was the first to implement this protocol exactly. So you see, for example, that the fraction of detection events, which is the places where the parity switched, is going up with the number of cycles. And that's not a good situation, because if it's going up with the number of cycles, it means that we're not actually clearing the entropy from the circuit, if you will, or we're reaching a situation where as time goes by, we're accumulating more and more errors, and we're not going to be able to preserve the state like this, okay? The second problem that we see is that as the circuit moves on, the leakage to the F state or the number 2 state is going up, okay? Probably for the same reason that we have here. The last thing that we see in this plot is that because the ancilla spend a lot of time in the 1 state, this leads to more decay. And the way you can see it here is basically what they did is they put either a logical 0 or a logical 1. And here the ancillas are going to flip from 0 to 1. And you see that there's this alternating zigzag pattern, okay? So we have all these problems. And all of these problems were kind of difficult to foresee if you were just trying to reason about this theoretically, okay? And some of them are unique to transmons. And this exemplifies a fundamental principle, which is that error correction experiments, they have to be hardware aware, okay? And the implementation of them must take into account the actual problems that occur during when you run the experiment, okay? And only a fully flexible controller where practically every parameter can be modified in real time can cope with these issues in any platform, okay? And this gives, and here we have with a quantum orchestration platform, a unique advantage, because if you have a generic controller where the feedback operations are very limited, or alternatively, you need to come up with your own FPGA code in order to do a more complicated feedback sequence, then if you run the experiment in the lab and you have a problem, the time you have to test a new idea on how to solve this problem is really unknown. It could be a day, it could be weeks because it's FPGA, okay? And then as any experimentalist knows, if you're going to need to spend a couple of days to test out a new idea, you're probably not going to test out that idea at all, and you're going to try something else. Okay, so this is a real barrier. However, if you're working with a quantum orchestration platform, the time to test out new ideas is minutes. Okay, and this can really make a huge difference in your ability to tailor the specific code that you're running, the specific protocols that you're running to the real problems that appear on your setup. Okay, so here, for example, we see reset. So here the reset is just created by adding this condition equal I larger than 0.03, where I is a measurement result. So it's really, really simple to add feedback in this case. And we're going to show more examples of this as we go along. Okay, so let's see how we improve the situation. Okay, so in order to do that, let's look at the QA code that's required in order to run this passive tracking experiment. So in the passive tracking experiment, what we're going to do is we're going to play a -y/2 over the ancilla. Then we're going to play 2 C phases between D0 and ancilla, and between D1 and the ancilla. And then we're going to play a y/2 on the ancilla. And this actually basically generates this set of gates, okay, the C naughts. And then we're going to measure, and we're going to save the result. Okay, so and we're going to run this in an infinite loop. Okay, so this is the QA code for the passive track. Now let's say that we want to add active reset. So in order to add the active reset, so that means that every time we're going to measure, we're going to apply a conditional operation that resets the ancilla. Okay, the only thing we need to do is to add this line to the code. Okay, that's basically it. So here we created active reset. And actually what we can see now is how does active reset help us? So for example, if we had a data bit flip error, then we're going to, instead of getting this alternating pattern, we're going to get a pattern of all ones, okay, from the same reasoning that we had before. And if we had a measurement error, we're going to get a single blip. So already less time is being spent in the one state, but I think even more importantly, the circuit is constantly being kind of like cleaned, okay, from so the entropy is not being accumulated. And actually, a recent paper by Google where they're implementing this reset, although not by control hardware, because of the specific capabilities of their quantum platform, shows that in this case, the detection event fraction stays constant throughout many rounds. So the active reset actually solved this problem. Okay, so, but this is one thing that you can do, and you can actually go even further and do something even more optimal, which is to do something called active parity tracking. Okay, so the idea in active parity tracking is the following. So let's say that we had here this measurement error. So now what we're going to do is first we're going to measure, and then we saw that we have an error, but we don't know what kind of error it is yet, okay? But we're going to wait one cycle, and then we're going to apply an X gate, okay? And so basically what happens is that in this case, it looks like we didn't do much, okay? We just basically converted what was previously 1-bit flip into 2-bit flips. But this is actually a very good idea for, first of all, because this actually gives the detection events, as they're called, directly. But there is another reason for this, which is that if we now have a data bit flip error, and what's going to happen is in the first case, we're going to detect the error. Then we're going to let the C0 bring the measurement on the ancilla qubit back down to the ground state. And then we're going to start applying X's all the time, X gates. So what we did is now we only have a single blip for the for this error, and actually, so now we have the qubits are spending even less time in the ground state, but there is an even more fundamental advantage to this scheme, because if you actually go through this, you will see that the conditional operation on this gate, okay, depends on a measurement that was done only 2 cycles before it, okay? And that means that there is ample time to calculate the pulse that you want to play here. And in fact, with the QOP, you can run this algorithm. You can do an active reset with no feedback time overhead. And you might be wondering how complicated it is to write this code. Well, the answer is it's extremely simple. You just have to modify this line of code and add these two, and it runs. Okay, and this has been experimentally verified. So so you can see that there is a really deep advantage to being able to do these things very quickly. But now a fair question to ask is, what about leakage to the 2 state or the F state? Well, this is an excellent question, and the answer is, well, no one knows, or no one has figured out yet how to handle this situation. But the point that we're trying to make here is that in order to figure out what the optimal thing to do, you probably need a very flexible control hardware, okay, that can handle any scenario, because the answers will probably not be known a priori, okay? Another thing that I want to discuss here is going beyond parity tracking, okay? So, and that is basically the fact that we can use the detection events on the ancillas to correct for drifts on the control pulses, right? So we know that when we want to run a long fault-tolerant experiment, we'll probably need to run it for a long time. And as the experiment is running, we'll need we'll have drifts in the control parameters of the qubits. And we need to be able to correct them online without destroying the quantum state, okay? So this can be, in principle, achieved using an online measurement of the ancillas. And here we're seeing a figure from another paper by Google. I'm sorry, there is no reference here, but this is another paper by the Google group. If you're interested, I can copy paste the reference for this a bit later. And we see here what they're showing us is that by deliberately adding errors, and for example, in this X gate, you can actually see this in the detection event fraction, and it's isolated to where the error was injected, right? So so it's in principle possible to do it, and because the OPX uniquely allows us to take any measurement outcome and to use it in feedback loop to correct for the amplitude of the pulses, the frequencies of the pulses, and almost any parameter that you have in your system, you can use this to do online correction. And to our knowledge, there is no other control hardware in the world that allows to do this currently. Also, another important, interesting situation is that recently, this is a very recent paper, shows that you can actually rigorously mathematically proves that you can track Pauli errors from these syndrome measurements. Okay, so this is a very interesting thing to explore. Okay, so just to recap, so what the main message that we're saying here is that when you're going to complicate experiments such as error correction and state preservation, it's really impossible to know a priori where the problems are going to be. And that's why it's critical to have a controller which is both flexible and has ultra-high performance. And we've shown various examples on how the Quantum Orchestration Platform can meet these requirements and even more than that. Okay, so I hope that I've convinced you that if you want to do a quantum error correction experiment and also other experiments on any platform, then the Quantum Orchestration Platform should be your choice. So thank you very much.
Thank you, Lior. Indeed, I will take over. And first of all, I would like to motivate basically the change of Qubit platform. So as you have seen in your talk, like the scalability of those surface code can be extremely complex. So I will just share my screen here. Yes. So as you may have seen, like the scalability required in terms of number of physical qubits to basically build the redundancy that you need to actually protect your information, it can be very cumbersome. So you saw before the example of the repetition code dealing with 3 qubits, which actually protects you for bit flip errors. But as you may see, the majority voting rule can be very quickly overrated, right? If you have two errors, like your code is useless. And so the proposal of extended repetition codes or surface codes are essentially there to add the redundancy and to dispatch it into non-local kind of physical systems. But now the question that we might ask is there maybe a better way to encode this redundancy? Perhaps could we think about systems, quantum systems that actually have a larger Hilbert space, which is as large as you would encounter with many physical qubits as transpons, and encode this redundancy within the same system? And one very good candidate for this is actually the quantum harmonic oscillator. And I will maybe motivate this for in a quick second. The idea here is that the important step is that the quantum harmonic oscillator has evenly spread states, energy states. And so why is this important? So first of all, a quantum harmonic oscillator are very well studied systems in quantum mechanics. There are actually multiple ways to build harmonic oscillators. You could take 3-dimensional superconducting cavities. You could take also mechanical resonators. There's a lot of possibilities. As you can see here, I've put some of examples of implementations of quantum harmonic oscillators. There's a lot of possibilities. So on top of having a technology that we know how to use and we know how to control, what is the purpose of having this system? So the main point I want to convey is that here in this harmonic oscillator, you have a kind of a ladder operator. This is why we would talk about bosonic modes. We have this kind of ladder operator that allows you to go to 0 to 1, 1 to 2, and 2 to 3, and et cetera, et cetera. And in principle, in theory, you could reach infinite number of states. For example, I will focus on the cavity modes. So if you have photons, for example, exciting your cavity by multiple photon excitations can lead you very easily to 1 or 2. And actually, the fact that it is evenly spread, you need only one control line to put you from one state to another. So it's very easy to reach. Now, also, there is another argument, which is basically what we can do here is a comparison with what happens in a usual setting when, so as the example of before, which involves many physical qubits. So of course, when you want to convey a full surface code with many physical qubits, you need a lot of control lines because you want to ensure that all the transpons, taking back the example of before, are actually controllable and measurable. So in terms of hardware deployment to control this system, it becomes very heavy very quickly. And on top of that, there is another constraint, which is the fact that each transpon qubit, physical qubit, will have its own noisy error channels, right? Each one of these is susceptible to decoherence. You may have relaxation rate, dephasing, and many other error channels. You could also leak to the F state, for example. So you have multiple errors that actually accumulate themselves as long as you build a redundancy. So reaching the threshold in this case to ensure that your information is protected can be very hard. Same goes for actually unevenly spread states, especially for the multiple, the number of control lines which are required to do that. So here in this case, you would have one single system, right? You would go 0, 1, 2, 3, 4, etc. So you would say, okay, I have one quantum system, which will be subject to a certain number of noisy quantum channels, but that's it. But the problem is now in terms of control lines, you must be able to address each transition separately. So the transition needed to go from 0 to 1 is actually not the same than 1 to 2 and 3 to 4. So you see that by this reasoning, we identified the quantum harmonic oscillator to basically both embed the redundancy that we need inside one physical system, which only contains a set of quantum channels. And typically, if I take the example of a cavity, the major noisy quantum channel that you might encounter is actually photon loss, single photon loss. But there are also all other kinds of channels that could occur, but you are basically limited in the amount of noisy channels, which does not accumulate as long as you increase the number of photons in your cavity. So this motivates the choice of a harmonic oscillator, and there have been multiple proposals to basically deal with what we call the bosonic modes. So trying to find nice encodings around this very large Hilbert space that is spanned by all these those Fock states. And the one I'm going to talk about today is the cat-qubit encoding. So the cat-qubit encoding, and I will motivate the name in a second, is based on the coherent states of light. So let me stay for the sake of simplicity in the cavity. So we will think about the electromagnetic bows. And so coherent states are defined, as you can see on the upper right of this slide, with a certain value alpha, which is a complex number. And you can see it's a quantum superposition of Fock states. So okay, now what are the properties of this state? When one of the most essential property is that this state is actually an eigenstate of the annihilation operator, which is so the ladder operator that allows you to go from 2 to 1 and 1 to 0. So it's basically like it is the channel that exemplifies the photon jump and the photon loss, essentially. So each time you lose a photon, it's like you would have this jump operator A, which would make you go down into the ladder. So, okay, so now what we can do is try to basically visualize what a coherent state is. And so to do that, we can use the Wigner function. It's a specific representation which acts as a quasi-probability distribution and which basically tries to assess what is the uncertainty you acquire on the quadratures of the field, of the electromagnetic field. So typically amplitude and phase, for example, here we usually know them I and Q components. And so in this IQ plane, so the idea is to mention that, of course, you might have uncertainty based on the Heisenberg uncertainty principle. And the nice property about those coherent states is on top of being eigenstates of the annihilation operator, there are also states which are minimizing the Heisenberg uncertainty principle. So actually, the blob, as you can see, is circular. And so when you basically increase drastically the value of alpha, so let's say you increase dramatically the value of alpha, actually you would do this by just increasing the number of photons in your cavity. The size of the blob, the size of the uncertainty becomes quite negligible compared to the actual value of alpha itself. So it's basically behaving as a classical state of light, meaning that you have a very, very low uncertainty, negligible, so you have quasi-deterministic kind of light state in this case. And now, this characterization of classical state of light motivates the use of cat codes, because now if I have alpha represented by this blob, on the IQ plane, I would exemplify minus alpha with this blob. And now I can, of course, use quantum mechanics to build quantum superpositions of those two coherent states. And so how would the Wigner function go? It would go like this. You would have a kind of an interference pattern going in the middle, which would basically exemplify the parity, the photon number parity of your state. So you can convince yourself that this quantum superposition with the plus state, which is what we call the even Schrödinger cat state, actually has an even parity, because when you do the superposition, you only are left with the Fock states which are even photon numbers essentially. And so the nice thing is that if you think about what I said before, those coherent states are called classical states of light. And here we are building a quantum superposition of classical macroscopic states of light. And why do we call them Schrödinger cat? It's because if you think about Schrödinger's thought experiment, you actually have two macroscopic states characterizing the cat, which are respectively dead and alive. And you can encounter the cat to behave quantum mechanically by having a superposition of those two classic macroscopic characterizations. So this motivates the use of cat codes. And now, why do we use this encoding? I will show you that this is particularly suitable to basically try to protect ourselves against photon loss channel. So let's take a look now about this encoding. So I will take two different even Schrödinger cat states. As you can see, the only thing that make them differ is actually the value of alpha. In the left, we have a certain number alpha, and you would have I alpha on the right. But it's essentially the same thing. Now, what happens when I evolve the photon loss? So we remember that coherent states are eigenstates of the annihilation operator. And so we are left with those states. So we have now odd Schrödinger cat states. And as you can see, what changed is the interference pattern. We have now a blue line instead of a red one. The red one would mean like you would have a plus one value on the Wigner function at this point in phase space, whereas now you would have -1. And this basically indicates you in which parity you're in. And now, if I do a smart thing by defining my logical states as follows, you remark that I actually am able to very easily distinguish when a photon loss error occurred or not. I just have to measure the parity of my cat qubit state to make sure that to understand that indeed a photon loss occurred or not. And then once I identified it, I can basically correct it. So you see, now we are also now again coming back to this notion of parity tracking, right? In another context, but it's also involving parity tracking, which is very interesting because it's something that comes a lot in error correction. The parity is a very interesting property to exploit, which allows you to not destroy the quantum state actually. And actually this experiment, so this encoding that I just presented you was done successfully by an experiment done in 2016 by no one else than imperfect, who is our current chief engineer at QM. And as you can see here, the experiment that he conducted at Yale was to extend the lifetime of a quantum bit with the error correction by protecting it against those photon loss channel, this photon loss channel. And it showed that using this protocol of error correction actually extended the lifetime of the qubit. So the correction of errors actually made a powerful impact. So at the time, it was a very, very important breakthrough. And as you can see, it's a very complex state machine that goes there. So I won't go too much into the details, but what I want you to remember from this is that actually parity tracking is an essential component of this scheme. And basically what allows in the state machine, which also used feedback so that we can do parity tracking and actually reset the state according to what we measured before, could be done through the parity. So now, having understood the importance of the parity tracking in cat codes as well, I will now briefly explain how it is done in practice. So the parity measurement is a bit different, of course, from what you would encounter in a transpond qubit, but it's actually interesting to notice that the way we would measure the parity is actually with the help of a transpond. So we're going to use here a dispersive interaction Hamiltonian, which you can see here on this part. And this dispersive Hamiltonian basically couples the photon numbers of your cavity to the state of the transpond. So having this coupling basically allows you in a very specific way to compute a controlled phase gate, which is displayed as follows. And now what I would like to do is actually realize this controlled phase gate so that I can extract the parity, which is symbolized by this operation. You can convince yourself that this is actually the parity operator, which if you apply this parity on an even state, like this will yield a +1 value. And if I measure it onto an odd Fock state, it will yield a -1 value. And using this circuit, as you see here, so I would do 2 pi/2 pulses separated by a wait time. I basically let evolve my qubit under this dispersive Hamiltonian. I will be able to compute this gate and extract from the information this phase accumulation that goes over here on the storage mode. And by a phase kickback mechanism, I will be able to retrieve this phase and actually map it on the state of the transpond. And so the outcome of this scheme is actually that you have a direct mapping between the photon number parity to the state of the transpond. And so in this encoding that I show you here, it depends on the sign of the pi/2 pulse that you do. So here you see it's a pi/2 on the y-axis, and the parity would correspond to, so the odd parity would correspond to measure an excited state, and the even parity would correspond to measuring the ground state of the transpond. So it means that, again, if I measure the excited state of the transpond, I know indirectly that a photon loss occurred. Whereas if I measure the ground state over and over again, it means that no photon loss was detected. Okay, so that's pretty nice. So we have this protection around photon loss channel, but as I said at the beginning, you have a very large input space. Your quantum harmonic oscillator, of course, if you are able to synthesize it in the coherent states, it's very nice, but there are tons of other processes that would actually get you out of this code space of coherent states. Like there's nothing that prevents you to actually go into a specific Fock state or any other state, which might not be a coherent state anymore. And so the issue here is that now we have to think about how can we add additional protection to this qubit against all those noisy channels. And so this is why we shifted from the first proposal, which was what was proposed in Nissim's paper, to a second proposal, which basically changes the encoding here. And as you can see, the block sphere is a bit different because now we encode the logical 0 to the plus alpha state and the logical 1 to minus alpha. And so now the even and odd Schrödinger cat states are respectively the plus and minus states of your block sphere. But now, okay, once we define this block sphere, what can we do with it? So actually, a bunch of researchers that have been focusing on developing what we call autonomous quantum error correction through two-photon dissipation engineering. So I want to explain to you like how this is done, because first of all, it's a very interesting pattern. And the goal will be to show you that the quantum orchestration platform can actually handle very easily this autonomous scheme on top of adding multiple constraints on qubit control. So the goal behind this two-photon dissipation process is, okay, the main idea is I want a form of error correction that not expects me to actually actively track the errors and actively correct them. I want to build something that will behave in a kind of autonomous way, in a sense that I can synthesize the natural dynamics. In this case, it will be dissipation dynamics that will, even if I encounter an error, if I wait a bit of time, it will automatically come back to my logical code space. And so you will have kind of a autonomous quantum error correction, meaning that you will eventually come back, that the error will not accumulate itself. It will naturally come back to the original states that you initially planned for your encoding. So the idea is that we realize that if you are able to synthesize this dissipation process. So as you can see here, I describe a master equation which symbolizes a two-photon dissipation process by this A squared over here. You can convince yourself that steady states of the solution are actually linear combinations of the plus and minus alpha states. What does it mean? It means that indeed I have found a dynamic where my logical states are actually the steady states of this equation. So I can rely on them during all the computation, because I know that if I wait long enough, I will recover them eventually. So now the question is, how do we build such system? And also, does it really prevent me to get any errors? So to understand more about how this dissipation process prevents you from getting any error, let's go very quickly to the semi-classical approximation. In the semi-classical picture, you could imagine this two-photon dissipation process acting as a double well potential. So as you can see here, if you are able to synthesize such dynamics, you will have this double well potential. And the attractors, so the two bottoms of the wells, are actually your plus and minus alpha state. So now, if I have any kind of error, which is, let's say, local in phase space. So I would, for example, be in my 0 state and I would quickly escape due to an unwanted error. The fact that this potential has this form as a well potential, it will naturally attract it back towards the alpha state. However, you should pay attention that those wells are not very well separated, right? There could be a process that brings you in the middle of this thing, and you would actually fall back on the wrong attractor. But falling back on the wrong attractor, what does it mean? It means that you're actually going from plus alpha to the minus alpha, which is actually a logical bit flip error. And so you want to avoid that. And so a very easy way to avoid this, to decrease the probability of having a wrong fallback. So as you can see, we will recover, thanks to the potential coherent superposition of alpha and minus alpha. It protects all of those linear combinations because those are steady states of the dynamics. But if I just increase the value of alpha, I increase the distance between the two wells. And I decrease, and this experiment was actually conducted by Raphael Lescan and Zaki Lektas in 2020. And they showed that you indeed incur an exponential reduction of logical bit flip errors when you increase the cat size alpha squared. So when increasing alpha squared, you have an exponential reduction. So how do you do this? It's very easy. Usually, you just increase the number of photons in your cavity. But you will tell me, is this for free? No, unfortunately, it's not for free, because you might have guessed that if you increase the number of photons in your cavity, you actually expose yourself to more potential photon loss channel. And photon loss channel in our encoding are actually phase flip errors. It maps, remember, the plus state, which is the even Schrodinger cat state, to the odd cat state, and vice versa. So now we have an error, a photon loss error, which is acting as a logical error in that code space. So this is not good. We would, of course, want something that can easily help us to find information by without destroying the quantum state at hand. So the statement that was done in this paper is actually that this exponential reduction of bit flip is still advantageous, because the increase of logical phase flip error rate with this value of the cat size is actually only linear. So you still can build this kind of bias towards one type of error, and it's still interesting. And so what can you do about phase flip error in this case? Well, you can still correct it with the repetition code. But now you realize that instead of having to correct both bit flip and phase flip errors, I can say, okay, I will develop a system and engineer a system that will automatically focus on the bit flip errors. It will automatically correct them just by the dissipation mechanism and my large number of alpha. And on the other side, I will only take care actively of one set of errors, which are the phase flips. So in practice, so as I mentioned before, this experiment was led in 2020 by Zaki Lektas and Rafael Lexcan. And here is basically a layout of the experiment. So let me break it down into a few pieces. There are actually 3 pieces to this scheme. So first, we have the storage mode, what we call the cat qubit. So this is basically the cavity that stores that information with coherent states of light. So this is easy. It's the way we protect it. On the left side, all of the things you see are basically decomposed in 2 things. It's all the devices that allow you to engineer this 2-photon dissipation process. So on one hand, you have what we call the buffer mode, which is another cavity, which is the property of having a very high photon loss rate. Why do we want this? It's because now if we are able to couple the cat qubit cavity to the buffer, the cat qubit will lose photons, and hopefully by pair, and I will explain how it is done by pair in a second. But it will mediate this exchange by pair with the buffer, and the buffer, having a very high photon loss rate within the environment, will quickly let get out all the photons that are acquired from the cat qubit itself. And now, okay, would you say, now how do I do this 2-photon dissipation? So I have to create some kind of non-linearity, because 2-photon dissipation is a non-linear process by essence, right? So this scheme, this loop, as you can see, which is called ATS, which is the contraction for a symmetrically threaded squid. It's a set of Josephson junctions that mediate a non-linear interaction between the buffer modes and the cat qubit modes. And actually, if you tune it, if you pump it at a very specific frequency, omega p, which is proportional to twice the frequency of the cat minus the frequency of the buffer, you actually create such interaction that induces exchange of 2 photons between the cat and the buffer. So this is very interesting, because now we are interested in like maximizing the rate with which the 2-photon rate will occur, because it will help stabilizing the code word. We will avoid escaping into the very large input space spanned by our quantum harmonic oscillator. We want to remain in this code space of alpha and minus alpha. And this is done by all this part. On the other part, we recover a transmon qubit coupled to a readout resonator, which is used basically for the parity measurement. Notice that in our own encoding, a parity measurement is actually reading out the cat qubit in the Hadamard basis. Because remember that if we are able to distinguish the parity, we are able to distinguish even Schrodinger cat state to odd Schrodinger cat state, which is essentially figuring out which state we have. So we destroy quantum information in this case when measuring out the transmon. Measuring out the cat qubit through the transmon. Okay, so now having learned all of this pretty technical stuff, I want to convey the message that here, AWS proposed a very nice embedding of all those concepts by saying, okay, we have this ability to build a very nice platform for for quantum error correction. And we want to embed this into a surface code architecture or repetition code in the one dimension. But of course, the repetition code will be done according to the error bias that will be done. You want to focus more on X-type stabilizer, which will try to correct for phase flip errors, compared to bit flip errors, which will be partially suppressed by your bias that you created at the beginning. And now the idea of this architecture is that you have this reservoir, which is the combination of the ATS and the buffer that I just introduced previously, which is coupled to multiple modes. And now you would ask, okay, but I have to be able to address all of those modes separately. And the way it is done is by basically addressing them through frequency multiplexing. So each of the storage mode here has a different frequency. And notice that there is another strategy here. We introduced the use of a readout mode, which is a bit different from the previous proposal, which was directly connecting the data qubit to the transmon. Here we have another cavity, which will be used only for the readout. And I will show you in the next slide how it works. So this is one step of the syndrome extraction for a single plaquette, which is in charge of measuring the X-type stabilizer. So again, X-type stabilizer focuses on detecting phase flip errors. So in this case, it will be photon loss channels in our encoding. So as you can see, there are mainly two parts, and I will cover them first separately. And you will understand at the end that indeed they are actually able to occur in parallel. So which is very interesting, because you would say, okay, there's a lot of stuff going on here, but in QA, it will be very easy to write this and to parallelize all the different things. So on the left side, you have a bunch of CNOT gates. So you have 4 data qubits coupled to an ancilla, and the mechanism is pretty similar to what Lior described earlier. So you want to do this parity check between all your data qubits such that you can assess what is the parity on your ancilla. Note that, as a reminder, all data qubits and the ancilla qubit are, so they are not cavities in the AWS proposal, they are actually mechanical resonators. So those are phononic modes and not photonic modes anymore. And we basically do this syndrome extraction. And on the other hand, we have another part which is purely focused on doing the readout scheme. So as I mentioned, we have this additional phononic readout mode, which is basically catching up the state of the ancilla through a swap operation. Let's forget about the deflate. It's not very important. It's just another tool proposed here to minimize the probability of having a photon loss, but it's not very important. The idea is that now, once I do the swap operation, this part works completely independently from this part. So as soon as I'm done with the swap gate, I can conduct my parity tracking here. So as you can see, it's very similar to what I presented before. It's the same sequence of setting the pi/2 pulse, doing this conditional phase gate, which does the phase kickback, and then measuring your transmon in the Hadamard basis. So you extract thing, then you do active resets, and you do it over and over again. And then you acquire like some kind of syndrome, some error history, and you can assess according to a majority rule or any other algorithm that would to basically try to assess if yes or no you have a flip that occurred in your system. And so while this appears, you can notice that this next cycle can actually begin. So it's very nice to see that everything is embedded at the same time. And also, let's not forget that this is active error correction, right, in the surface code. But behind the scenes, we also want to keep stabilizing each of the data qubits through the pumping by the ATS to protect it against bit flip errors. So we have all of this going on kind of at the same time. And there is some kind of scheduling stabilization schedule. There is some stabilization schedule that occurs in this case. And the main idea is to say, okay, I won't want to address too many qubits at the same time because there might be any crosstalk. So I want to basically focus it by pairs. And as you can see, so it's decomposed in basically 4 blocks, 6 in total with the initialization step and the readout scheme. But it's decomposed in 4 blocks, which are corresponding to all the 4 CNOT gates. So you have photon CNOT number 2, number 3, number 4, and number 5. Okay, so now I want basically to shift towards some QA code, and I will go through the IDE. So I will share my screen on the pie chart. Here we go. So the QA code is a bit involved, but I want you to basically keep the main parts here. So can you see the pie chart, by the way?
Yes, we can.
Yeah, amazing. Thanks. So the main idea is that you want to separate the stabilizer scheme, so which is going to compute this bunch of signals that I showed you earlier, and the readout. But now in QA, what is very nice is that even though I write those things in the two different statements, the compiler will automatically try to allocate the resources such that everything is done as much as possible in parallel. And so, of course, as we've seen before, Gal has presented it in previous session, we have those QA macros. And each of those can, of course, embed a bunch of statements. So let's take a look very quickly on the stabilizer scheme. So here, as you can see, I reproduce very naively all the time steps, writing the C0 between the elements that are composing my plaquette, but also not forgetting that in the meantime, I'm also stabilizing passively through the pumping of the ATS, my cat qubits. And I do all these time steps very easily and without diving too much into the details of the control. If you're interested, I can elaborate more a bit later, but the main idea is to identify here the simultaneity of the process. And I can now go down to the readout part, which is also occurring. And as you can see, the elements, the quantum elements that are involved in this case are pretty different to what we encountered in the previous function. Here, we only focus on doing operations on the transmon and the readout resonator. And here, as Lior showed before, we could easily add an adaptive parity tracking, as we mentioned before, to optimize the readout fidelity and ensure that the protocol is optimal. So that's about it for the QA code. If you're interested, I can dive more into the questions, but in the meantime, let me quickly come back to the presentation to do a quick summary. So yes, it should work. No, it's not working. Sorry, 1 second. Yes, now it should be good. So okay, this is, yeah, can you see the summary slide? I'm not sure if I'm sharing correctly. There is some kind of bug on my computer, I apologize. Okay, I will. I assume that you see the slide. Yeah. Okay. Cool. So, okay, very quick summary of multiple challenges that arise that I have not covered fully in this talk. But on top of the simultaneity that requires, of course, lots of threading allocations and so forth, the compiler does that. Does everything for you, so you don't have to worry about anything. And there are multiple other features that are actually very needed for specific implementation, but that they can be all very easily accumulated with the interface of QA. Frequency multiplexing is one of them to address multiple qubit. We haven't talked about this real-time phase modulation, but it's basically the way that C0 gates are actually computed in this cat qubit paradigm. And we, of course, need, if the phase is important, we need to ensure that phase lock is doable between various control lines. So overall, I would say that on top of what Lior mentioned earlier, we have lots of current challenges that might incur for every qubit platform, and that we are, and the OPX tries as much as possible to break it down to many different levels, which are all addressable eventually through the software due to its own construction. So I convinced you that the versatility and the universality of the quantum orchestration platform for handling multiple quantum orchestration scheme with very promising platforms can be ensured and paving the way for fault-tolerant quantum computation. So I will stop here and thank you for your attention. So diving into the second session, so now we're, let's forget everything that we learned so far. Well, hopefully not everything, but now everything that was mentioned before has nothing to do with what we encounter right now. So the message that I want to convey is that on top of course, the critical importance of quantum error correction for ensuring scalability in our quantum systems, we today have encountered some proofs of quantum supremacy in the past 2 years. Google has done it, the Chinese team has also done it in the past. And so we are on the verge of perhaps envisioning first applications emerging with our current available hardware. However, of course, there are multiple challenges that have to be addressed with what we call the NISQ devices. So the NISQ standing for noisy intermediate scale quantum. They require specific considerations, right? Because first of all, they have limited number of qubits. So as Gal mentioned in the previous presentation, there are roadmaps to scale up to 1,000, perhaps even more in qubits in the next few years. But today we are basically handling processors which are between 100 and 1,000 qubits, which is still very small and actually not comparable to the requirements of big surface codes for fault-tolerant quantum computation. The second constraint, of course, is the coherent and incoherent kind of errors that arise in the hardware. So we have to account for this. And if we want to compute real algorithms based on this, we have to account for limiting depth of the quantum circuit, because the error will make your circuit worse and worse as soon as you want to make it very large, very deep. And finally, there are also in certain platforms problems of connectivity. Actually, decomposing a set of concrete gates can be very complete unitaries can be very difficult to decompose into a set of unitaries. And again, we might have enhanced and increased circuit depth, which is not suitable for NISQ applications. So the way of thinking in the past few years was to say, okay, can I think about compensating for those current flaws, because those are flaws of the current quantum hardware, with the resources that I know very well, which are classical resources. So can I think about algorithms which basically combine classical resources, which are very reliable, and quantum computing, which might already in the NISQ era indicate some very interesting stuff. So one example, one subclass of those hybrid classical quantum algorithms are variational quantum algorithms. And why do we call them like this? It's basically because they follow up from the variational principle in quantum mechanics, which basically states that if you are given a quantum system which behaves under a certain Hamiltonian, if you compute the expectation value of this Hamiltonian in this quantum state, like the configuration based on your qubits, for example, the variational principle states that this configuration will always yield an energy which is higher or equal to the ground state. And more importantly, if you find an expectation value that is equal to the ground state, it means that the state size that you encountered is actually the ground state of your system. And now the whole idea is to basically figure out that the main idea is to figure out how you can map interesting problems, optimization problems, machine learning, or any kind of applications on these devices, and to map it to a ground search problem, which is something that physicists love to do, some kind of mapping to a physical problem. So the way we do this is actually by introducing some parameterization. And the main idea is that you want to compute a cost function that will take exactly what this expectation value, and it will now be parameterized by classical parameters. And as you can see, we want to prepare a quantum circuit on the right here, which is, of course, we're going to prepare a specific quantum state parameterized by classical parameters. And we're going to use the classical computer to update those parameters in a way that we are getting closer and closer to a quantum state that yields the optimal configuration, yielding the minimum energy of the system. Okay, so now let's dive very briefly to applications. So as I mentioned, you could have machine learning, you could have ground state search, quantum simulation. You could have also other kinds of applications, which are very well summarized in the very nice review by Cerezo et al. It's a really nice review covering all there is to know about variational quantum algorithms. But today I want to focus on a specific subset, which is combinatorial optimization, and focusing in particular on one type of algorithm, which is considered as one of the best candidates for demonstrating useful quantum advantage, which is called the quantum approximate optimization algorithm, so QAOA for short. And I basically want to show you very concretely how we can leverage the architecture, the full architecture of the Quantum Orchestration Platform to actually run such algorithm. And you'll see that it involves, as any hybrid classical quantum algorithm, lots of communication between the classical and quantum resources. And the QOP is an ideal candidate to do those communications. So first, a bit of context. The max-cut problem is basically the canonical problem that QAOA aims to solve. It's a combinatorial optimization problems who can be summarized as follows. So you are given a graph with a set of nodes and edges. And what you want to do is find a partition of the nodes. You want to separate it in two sets, such that you will the cut that is induced by this partition will cross as many edges as possible. So here, for example, if you see in this drawing, the cut that is displayed here will cross 1, 2, 3, 4, and 5 edges. And of course, we could imagine of cutting the set in two. I could do a cut like this. It would yield only a cut of 2, which would not be very smart. And the idea is to basically find the best cut. And actually, this problem is NP complete. When you scale it on very large instances, it can be. It is not. There is no classical algorithm that allows you to do this in an efficient way. So we hope that the QAOA can provide approximate solutions of the best of the maximum cut through the use of the quantum computer. So first, we have to map to find a cost function. So this classical, you can convince yourself that this classical cost function, x here are a set of variables, and we iterate over the nearest neighbors, so the nodes that are connected by an edge. You can convince yourself that this is the cost function that for the maximum of this function will yield the max cut. And the whole thing here is that I want to map this to a quantized Hamiltonian, which you can see here. So we have something proportional to sigma z operation or identity. So we have a diagonal Hamiltonian that is going to encode a problem. And this is done easily by just doing some kind of mapping. We quantize the cost function by saying that xa now becomes an operator, which is identity minus sigma z over 2. Okay, so now let's dive into the algorithm itself. So the algorithm is again all centered around this classical quantum subroutine. So the quantum computer will actually be used as a sampler for potential bit strings, because at the end of the day, what you're going to measure are sets of bits. And what you want to do is maximize the probability of finding a bit string, which is going to give you the optimal partition in your max cut problem. So you have a quantum circuit here, which is displayed as a series of blocks. So as you can see, we have one block up to the block number P, and each of those blocks are actually parameterized by classical parameters, which are named here gamma 1 and beta 1, up to gamma P and beta P. So those are classical parameters that are going to be fed out inside the classical optimizer. The idea is that I will compute my solution, call the quantum circuit, run it multiple times so that I can do some kind of sampling. Once I do the sampling, I can evaluate my cost function based on all the bit strings I evaluated, and see. The cost function is, as mentioned in the beginning, the expectation value of the Hamiltonian. So the Hamiltonian deduced from the max cut problem. And from this, I will try to use a classical optimizer to optimize those parameters gamma and beta and refeed them to launch a new program every time. And you can convince yourself that this quantum circuit actually yields this parameterized quantum state. And the motivation here, without spending too much time, is actually based on the adiabatic theorem, where basically try to discretize the adiabatic pathway that will allow you to navigate from a very easy Hamiltonian, which we call the mixer Hamiltonian, spanned by this HM, those sets of single qubit rotations around the x-axis, and to slowly converge towards the ground state of your cost Hamiltonian, which is our target. So of course, there are many things that could be addressed, but I want to focus on one specific part of this problem. And the part is this reloading the program every time. So this parameter update that has to occur, it's very inefficient because usually, as you can see, the structure of the circuit is fixed, right? The only thing that changes are actually only classical parameters. But once I have my decomposition of these unitaries, changing parameters is usually very easy. And the way it was done so far in many systems, I actually worked on this QAOA for almost a year on IBM platforms, for example. And it used to be that you had to relaunch a new program and to launch a new job for each of the parameters that you set. And so this would induce a significant latency of communication for basically running your full experiment and doing the full optimization schedule. Whereas the Quantum Orchestration Platform proposed a very different proposal. And I basically want to focus on this basic example. So I will quickly shift back to my code, Right. So, okay. So first, let me demonstrate the QOP program in a nutshell. The QOP program is basically the quantum part, right? So you have here the first part of the circuit, the cost Hamiltonian evolution, then the mixing Hamiltonian, and finally the measurement. So nothing fancy here. Won't spend too much time on it. But what's the interesting part is what happens before. So how do I initialize my program? So what I introduce here is a set of assignments. So this is my way of loading my parameters. And as you can see here, I basically call some variable which are called IO1 and IO2, which basically is an abbreviation for input-output variables. And what are those? So those are essential those are memory slots available straight from the quantum machine instance that you declare, where you can pass Boolean variables or floating point variables or integers. And you can do that while the program is still running. So the program here is basically embedded into an infinite loop. Each time, like here, I will do a for loop to basically sample out for multiple sampling expectation. But before running this circuit, I want to make sure that my parameters are updated. So this is how I will load the array, by basically inserting my variables into these memory slots introduced here. And how do I do that? So I can do this through the client PC. So using a classical Python function, and the quantum machine instance, which serves me as the communication between what's happening in the OPX. It goes through a server, and I can send and retrieve information using those input-output variables. And to give you an idea, so here, as you can see, I'm checking that the job is paused. So I have pause statements inserted within the program. And once I'm done loading the parameters that I need, which are given by my classical computation, I can just resume the job and launch again the new protocol. To give you an idea about how much time you can gain through this protocol, when you basically try to upload up to 400 parameters with those IO variables, if you take both compilation time of the program, the successive loading of those 400 parameters, and you retrieve the results, it takes approximately all the execution, just the program for loading these parameters takes approximately 4 seconds. Whereas launching a program multiple times with every set of parameters, so you would launch, in this case, 200 programs, this would take about 1 minute. So you have a significant reduction of latency. And of course, it can also be related to the server communication, all of the factors that could be drastically improved. But the IO variables are communicating much less information, because when you launch a new program, you actually have to recompile the new thing. The compiler has to do the job of making sure that the execution can be done, whereas the circuit has not changed. So it's very inefficient. In this setting, you basically increase the rate at which the classical resources can communicate with the quantum resources. So this can be very interesting. And on top of that, you can, of course, very easily add all the improvement that we showed before on top of the circuit. So of course, active reset can be very easily done. And note also that I can retrieve the cost function evaluation in real time. So I can do classical processing in real time. So meaning that I can keep calculating on the fly my cost function while I'm still running the circuit. So I'm acquiring data for each sample, and I can basically add the contribution of each sample while it's still running. So I reduce, again, by staying as close as possible to the hardware, the latency that I acquired for related to classical calculations. So a lot of improvements can be, of course, done, and we would think about extending this for many other algorithms. But the main idea we want to convey here is that actually the improvement of classical quantum communications can be both done by real-time capabilities, but also by smart use of a nice architecture embedding the full abstraction of the quantum computing stack. Okay, so coming back very briefly to the slides. So let me come back. Where is it? Yes, here. Great. So in summary, we see that the QA in QA benefits from real-time added features. So active reset is one of them. On the fly cost function calculation, execution time reduced by these optimized communication schedules between the client PC and the OPX, so through the input-output variables. But the question now is, can we do more? And actually, so what I wanted to convey here is that there are also very interesting grounds for research on those variational quantum algorithms by using pulse control, which is very easy to do in QA since it's a pulse level programming language. So there's been this proposal done by a Google team. As you can see, Google is present in many fields, from error correction to NISQ approaches, that basically tries to break down the usual abstraction layers we created with the circuit model by saying we have the circuit level and the pulse level that have to be completely separate. What if we could think about building some kind of new solutions, new hybrid kind of circuits, which would embed parameters from the circuit level, as you have seen before with the QAOA, but also pulse level parameters that could be in QA updated in real time. I could think here about the amplitude, about the duration, about the phase, the frequency. All of these parameters could be updated in real time and could actually perhaps leverage more kind of optimal control theory and perhaps increase the performance of the algorithms. So it's actually a very interesting research statement, because so far in quantum computing, we try to relate usually as much as possible to the classical computing version, where we really try to build every stack separately. But perhaps in a NISQ approach, what we want to do is extract to push the limitations of our current hardware. So we have to be, again, hardware aware of what's happening, what are the dynamic processes that are occurring on the hardware, and keep pushing this even on the algorithmic level to enhance the performance of all the computations. So this is why we believe that the quantum orchestration platform can really be a central component of a standard quantum computing stack by basically using the QOP to run simultaneously quantum algorithms, NISQ, or in the future, hopefully fault-tolerant algorithms. You can, of course, perform calibration experiments for your quantum hardware. You can also have an architecture which really tackles all the resources from the classical resources for processing and real-time processing, all up to the quantum resources itself. And the metaprogramming is also a nice way to conceal all this complexity behind the gate level and to perform the crossing between layers of abstraction that can actually help you build better hardware efficient protocols. And finally, through this last section of opening research towards this quantum optimal control VQA mixing, we hope that the QOP can serve as a nice platform for conductive, ambitious research. And on that note, I think I'm done. I hope I haven't lost you too much on the road, but I'm sure you agree with me that those are very exciting times for quantum computing, and a standardization for a community of researchers and talented researchers is needed. So thank you very much, and up for question now. So I see one question in the chat, so I will just stop the screen sharing. Okay, so for VQAs, how would you handle the reloading of new waveforms if you embedded optimal control in the frame of variational algorithms? Would you have time to relaunch the full program every time? So, okay, so it's a very good question. So the question is, if we are indeed required to update all the waveforms, would we have to relaunch a program every time? So actually, no. We have the ability in the quantum orchestration platform to pre-compile jobs. So we can separate the compilation step of the program, which, as you have seen in QAOA, for example, is very common. And you can just override the waveforms. And so this can be also done dynamically through the uploading in the client PC. So you can perform a classical optimization of the waveforms through quantum optimal control algorithm using the packages that are suitable for this. For Q control, for example, does extensively this post-control research. And you could just use the QOP to load the waveforms while the program is still running and prepare the next iteration like this, without having to recompile and relaunch the full program from scratch. So you get an economy here on the execution time. There is a second question on the quantum error correction with cat codes. So do you need direct control of the cat qubit to perform quantum gates? So the very interesting answer is that the answer is no. We don't need to have a control line directly connected to the storage mode to perform C0 gates and X gate. Actually, what has not been experimented before, but which is very promising, is that we can compute all kinds of gates using dissipation engineering with the buffer, the buffer drive. So this is very interesting because we can ensure indirect control through the buffer and compute all sorts of quantum gates. But note that most of those gates, like X gate and C naught, have not been implemented yet. Experimentally, so we have an answer to compute them, but it's currently an open question of what are the full hardware requirements to compute such gates. But we know that it involves, for example, real-time phase modulation, as I briefly mentioned in the talk, and this is easily doable through a feature which is called frequency chirping in QA. Okay, I think if there are no more questions, perhaps no, I think it's done. So with this session, I would like to thank you again, and I will take this time to introduce the next session, which is going to happen a bit later down the road. So the name of the session will be showcasing feedback and real-time classical processing in different QPUs, which is going to happen at 3:15 past 3 p.m. So the basic idea is that after showing how real-time feedback and classical processing play a key role in quantum algorithms, the previous session, so in our session, in this next session, we will show how these components are also crucial in the preparation and calibration stages of quantum system. The case of controlling silicon-based quantum dot qubits and taking advantage of feedback capabilities will be presented first. This will be followed by a demonstration of how the QOP can be used to move atoms in tweezer traps and arrange the initial arrays for Rydberg QPUs. We will also show how the low latency feedback architecture of the QOP can allow for the generation of gates that are immune to laser intensity fluctuations. So the part one will be ensured by Will Gilbert from the University of Sydney, on-demand electrical control of spin qubits. And the second part will be conducted by Ramon, who is here right now, on preparing arrays and optimizing gates in Rydberg platforms. So thank you very much for your attention, and see you soon for the next session.